A spacecraft leaving Earth does not start from a standstill. Before its engines do anything, it is already traveling around the Sun with Earth at about 29.78 kilometers per second, or roughly 66,600 miles per hour. That inherited speed changes almost everything about how we move through the solar system. If the goal is to escape the Sun from Earth's distance, the spacecraft can use the motion it already has and add more speed in the same direction. In an idealized case, adding about 12.3 kilometers per second is enough to reach local solar escape velocity. But suppose instead that we want to turn the spacecraft 90 degrees and send it far above the plane where the planets orbit. Keeping the same speed while changing its direction by 90 degrees would require a velocity change of about 42.1 kilometers per second, close to 94,200 miles per hour. So in this deliberately simplified comparison, turning up can require more than 3 times the change in velocity needed to escape the Sun. That sounds wrong at first. Empty space above the planets does not look like something that should be difficult to reach, while escaping the Sun sounds like the harder journey. The reason is that the spacecraft is not fighting empty space. It is fighting the direction of the motion it already has. To escape, it can add energy along its existing path. To head sharply out of the planetary plane, it has to redirect a large amount of sideways velocity that came with it from Earth. These numbers are not universal mission costs. 12.3 kilometers per second is not a complete launch budget for escaping the solar system, and 42.1 kilometers per second is not what every high-latitude mission has to spend. They describe 2 specific idealized maneuvers that make the underlying problem easier to see. Real missions find more efficient ways to change direction. Ulysses used Jupiter's gravity to enter an orbit inclined about 80.2 degrees to the Sun's equator, while Solar Orbiter has repeatedly used Venus flybys to increase the angle from which it observes the Sun. Instead of supplying the entire change with propulsion, these missions use the motion and gravity of planets to reshape their trajectories. But even then, the basic problem remains. Going up in the solar system is not difficult because there is something blocking the way. It is difficult because a spacecraft leaving Earth begins with an enormous sideways velocity, and changing the direction of that velocity can cost more than simply adding to it. By the end of this video, you will understand what up actually means once we leave Earth, why traveling far outside the planetary plane can be surprisingly expensive, and how spacecraft use planets to make turns that would otherwise require enormous amounts of fuel. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. Up feels settled while you are standing on Earth. Wherever you stand, the local vertical points along a line running through you and Earth's center. The direction away from that center is up. The direction toward it is down. So up is radial. It belongs to a location beside this planet, rather than to a permanent axis drawn across space. That also means people at different places on Earth do not share one set of parallel vertical lines. Each person's vertical follows the radius through that person's position. Their directions can differ while each remains physically valid. The word local carries that distinction. It names the vertical where the observer is, with Earth as the reference body. Earth's gravitational environment gives this direction practical meaning. For someone on the surface, gravity supplies the familiar downward direction, and the opposite radial direction supplies up. Altitude then describes how high something is in relation to Earth. A balloon overhead, an aircraft climbing, and a spacecraft just leaving the ground can all be described through that Earth-centered relation. The label is chosen because the nearby planet makes it physically useful, not because someone happened to draw a convenient arrow. A launch can therefore begin by going upward without any confusion. During that local part of the motion, engineers and observers can describe the spacecraft's height and direction relative to Earth. Yet the definition remains tied to Earth throughout. Moving away does not make Earth's gravity vanish at a boundary. and it does not make the original vertical false. It changes which reference answers the question being asked. When the question becomes the spacecraft's trajectory through the solar system, its immediate height above Earth is no longer enough. An Earth-centered radial line can still describe where the spacecraft lies relative to Earth, but that line cannot provide one universal up for the entire mission. The spacecraft's motion must be stated relative to the body and path under discussion. That reference must be declared before the direction has a precise meaning. To make that declaration precise, a trajectory description needs more than the spacecraft's name and a direction. An ephemeris state gives its position and velocity relative to a selected center, using a specified coordinate frame. Neither part is frame-free. Without the center and frame, those values are missing the information that gives them physical meaning. This explains why two coordinate descriptions can differ without disagreeing about the spacecraft. An Earth-centered state and a Sun-centered state describe the same physical object from different selected centers. Changing the coordinates does not push the spacecraft onto another path. It changes the numerical account used to answer a particular question, so the choice has to be named. Once a spacecraft has escaped Earth and the question concerns its travel around the Sun, a Sun-centered reference is commonly the helpful choice because the motion being discussed is heliocentric. The Earth-centered description has not become false. It can still say where the spacecraft is relative to Earth. The Sun-centered description is better matched to a question about the spacecraft's path around the Sun. You choose the center according to the relation you need to describe. The spacecraft still has only one physical motion. Above requires one more piece of structure. Naming a central body establishes what the position is measured from, but it does not by itself establish which direction counts as above. That direction must also be measured from a declared plane. A claim that a spacecraft is above something therefore remains ambiguous until it names both the body at the center of the description and the plane used to separate above from below. These declarations make a trajectory statement interpretable, but they do not supply the trajectory. A real ephemeris state still depends on its specified conventions and conditions, and this simplified account cannot stand in for that solution. It gives us the minimum needed to ask the question cleanly. Relative to which body, in which frame, and from which plane is the spacecraft said to be going up? Once the center, frame, and plane have been named, the spacecraft still needs two different descriptions. Its attitude tells you how the vehicle is oriented, which way its body and anything fixed to it are facing. Its velocity tells you how its position is changing through the chosen reference frame. The first belongs to the direction of the spacecraft itself. The second belongs to its translational motion. They can point in different directions at the same time, because facing one way does not require traveling that way. Suppose the spacecraft rotates until its nose points above the plane on a sun-centered diagram. That rotation changes its attitude, but by itself it does not rotate the sun-centered velocity vector, carrying the spacecraft along its heliocentric path. The vehicle may now face across, along, or away from its direction of travel, while continuing with the same translational state. So a drawing of a spacecraft tilted upward cannot establish that its trajectory has begun to rise. It shows where the vehicle points, not a new path around the Sun. Attitude still has real consequences. Turning the spacecraft can aim an instrument toward its target, changing what the instrument can observe without changing the vehicle's velocity. It can also aim an engine, and that is where orientation can begin to affect motion. The engine applies thrust in the direction selected by the spacecraft's attitude, connecting the way the vehicle faces to a force on the vehicle. Even then, the turn is not the trajectory change. Thrust must act over time to alter the velocity, and the spacecraft must have the propulsion capability to produce that change. Firing after the turn can add velocity in the engine's chosen direction, producing a new sun-centered translational state, and therefore a different heliocentric trajectory. How much the path changes depends on the velocity change the propulsion actually delivers, not on the angle through which the spacecraft happened to rotate. Pointing can prepare the maneuver and determine the direction of the thrust, but it cannot provide the change for free. The quantity that has to be specified is the resulting change in velocity. That resulting change in velocity still needs a direction, and the direction needs a reference. In orbital mechanics, inclination is an angle measured from a stated reference plane. An inclination by itself is therefore incomplete. If someone gives you the angle but leaves out the plane, you know how large the tilt is supposed to be, but you do not know what the path is tilted relative to. The comparison plane is part of the quantity, not a detail that can be supplied later. This also means that a path does not carry one inclination that remains meaningful under every possible description. Change the plane used for comparison, and the angle describing the same path can change with it. That does not make inclination subjective. It means the measurement has a defined starting surface, just as any angle must be measured from something. Before asking whether a spacecraft can move above a plane, we have to name the plane whose above and below we mean. A real heliocentric trajectory needs more than that plane. It depends on the spacecraft's state at a particular epoch, where it is and how it is moving at the stated time, together with the ephemeris information needed to place the relevant bodies at that time. A broad label such as upward does not provide those conditions. Two requests that sound directionally similar can describe different trajectory problems if they begin from different states or refer to different times. None of this makes up wrong in conversation, and a simple question does not have to become a full mission design. It does mean that the practical version of the question has two parts: which plane supplies the comparison, and what change in the spacecraft's velocity is intended to produce the requested path. Those questions preserve what the speaker is trying to ask, while replacing the loose direction with quantities that can be specified. Once the plane, epoch-specific state, and intended velocity change are stated, difficulty can be discussed without pretending that space has a fixed ceiling. Until then, "Can the spacecraft go up?" combines several different choices in one word. The plane we need can begin with Earth's path around the Sun. An orbit lies in a plane, and the plane of Earth's orbit is called the ecliptic. That name gives the familiar flat solar system diagram a specific geometrical basis. The page may show the Sun in the middle and the planets moving along nearly horizontal tracks. But the horizontal direction does not come from space itself. It comes from the choice to draw Earth's orbital plane flat on the page. That choice also gives astronomers a shared baseline. When the orbit of a major planet is described as tilted, its inclination can be compared with the ecliptic rather than with an unstated idea of level. Each orbit can then be described against the same plane. The comparison does not require every major planet to follow Earth's plane exactly. It requires the reference to be named, so the angle assigned to one orbit means the same kind of measurement as the angle assigned to another. Once the plane is fixed, above can be made precise as well. Geometry supplies a direction called the normal, which points straight away from the plane rather than along it. A spacecraft moving in that direction would be increasing its separation from the ecliptic plane. Its position and motion could be measured relative to Earth's orbital geometry, instead of being described as though it were climbing toward the top of a universal map. The ecliptic remains a reference convention, not a sheet of material surrounding the Sun. There is no surface there for a spacecraft to pass through, and choosing one side as above does not give the cosmos a fixed ceiling or floor. It simply states which plane is supplying the comparison and which direction counts as away from it. That precision leaves one distinction unresolved. The normal to Earth's orbital plane defines ecliptic north, but it has not yet been shown to be the same direction as solar north. The ecliptic gives us one exact answer to above which plane. It does not establish that every physical feature of the solar system must use that same plane. The Sun supplies another direction through its own rotation. As it turns, its rotation axis defines two poles, solar north and solar south. The plane halfway between them is the solar equator, so when solar scientists describe latitude on the Sun, their coordinate system comes from the Sun's spin. It doesn't inherit north and south from Earth's path around the Sun. That gives us two physical planes with different origins. The ecliptic follows Earth's orbital plane, while the solar equator follows the Sun's rotation. They are close, but they do not coincide. The solar equator is inclined by about 7.25 degrees to the ecliptic, That angle is the measured tilt between the planes themselves. It is not the latitude of a spacecraft, an inclination already reached by a mission, or an angle that every solar observation automatically shares. 7.25 degrees may sound small, yet treating it as zero would merge two coordinate systems that answer different questions. Start from the ecliptic and north means the direction perpendicular to Earth's orbital plane. Start from the solar equator, and north means the direction along the Sun's rotation axis. Neither definition replaces the other. Each is exact only after you say which plane generated it. This changes how the word polar has to be read. A solar polar trajectory, or observation, is described in relation to the Sun's rotational geometry. If its angle is instead measured from the ecliptic, the number belongs to a different reference plane. You cannot move that number from one description to the other, while silently keeping the same meaning, because the two planes begin about 7.25 degrees apart. The same caution applies whenever an angle appears beside words such as north, south, latitude, or inclination. An angle measures separation from a stated axis or plane. It does not carry its reference system inside the number. For solar science, the object named in the description tells you which geometry is being used. Solar north belongs to the rotating Sun, while ecliptic north belongs to Earth's orbital plane. A plain label without that physical source leaves the direction incomplete. A third plane names another physical source. The invariable plane is defined from the total angular momentum of the solar system. It takes the system's combined orbital motion as its starting point, rather than Earth's orbit or the Sun's rotation. This dynamical reference describes how the solar system's motion is oriented when considered together. The total angular momentum supplies a direction, and that direction defines the normal to the invariable plane. So this plane is not selected because it is easiest to draw on a chart, or because an observer happens to be standing on Earth. Its reference comes from the system whose motion is being described. If you want to describe Earth's orbital geometry, the ecliptic still has the relevant normal. If you want the orientation of the rotating Sun, the solar rotation axis is the relevant direction. For the combined orbital motion, the invariable plane provides the corresponding reference. Those three choices do not have to point north in exactly the same direction. The normal to the invariable plane can differ from the ecliptic normal, and it can also differ from the Sun's rotation axis. Calling any one of them north therefore answers an incomplete question until the associated plane or axis has been named. There is no single normal that must replace the other two. Each belongs to a different physical description. Even the invariable plane needs context when it is written as a numerical orientation. A calculation supplies a realization for a stated epoch, and understated modeling conventions change that context, and the numerical representation is no longer being given under precisely the same conditions. An exact angle without its epoch and model can therefore look more universal than the calculation allows, as though it named one context-free and unchanging direction. That dependence does not make the reference arbitrary. The physical definition still comes from the solar system's total angular momentum. The epoch and conventions tell you how a particular calculation has represented it. Plain choice can now be matched to the question: Earth's orbit, the Sun's spin, or the system's combined orbital motion. The word north follows that choice. An ecliptic inclination compares a path with the reference plane of Earth's orbit. For a claim framed around the planetary plane, it asks how far an orbit or route leans away from that reference. Its north comes from the normal to that plane. It does not tell you how close anything is to the Sun's north pole. For that second question, heliographic latitude is the appropriate measure. It places an object relative to the Sun's equator, so its north is tied to the Sun's rotation rather than Earth's orbit. If you are asking where a spacecraft lies relative to the solar equator, or whether it is positioned toward a solar pole, this comparison answers you. Exchanging one angle for the other would change the physical question. One concerns a path against Earth's orbital reference plane. The other concerns a position against the solar equator. A system-wide dynamical question can call for the third plane. There, the reference comes from the solar system's combined angular momentum. You are no longer choosing Earth's orbit as the baseline or using the Sun's equator to locate an object. You are comparing behavior with a plane defined by the system's orbital motion taken together. The angular momentum plane therefore answers a question about the solar system as a whole under the epoch and modeling conventions attached to its calculated orientation. So a directional claim needs its stated angle, the plane from which it is measured, and the physical question being answered. The same route can receive more than one valid description because each compares it with something different. Those descriptions are not rival answers to one measurement, and the geometry has not disappeared. North names the side selected by a particular plane's normal. Once the reference is named, the apparent dispute becomes a reading problem. Is the claim about a path relative to Earth's orbit, a position relative to the solar equator, or system behavior relative to combined angular momentum? With that settled, a physical doubt remains. Do the major planets themselves form the flat sheet that planetary plane language seems to suggest? The major planets do form a flattened pattern, but the word sheet can make that pattern sound more rigid than it is. Compare their orbital planes with the ecliptic, and the orbits gather near that shared reference. They do not point in a random spread of directions. The ecliptic gives us one plane against which the tilts of the major planets can be compared. That plane is a geometric reference, not a physical surface running through the solar system. It is not a cosmic horizontal either. An orbital inclination only has meaning relative to the plane chosen for the comparison. Using the ecliptic lets each major planet's inclination answer the same question. How much is this orbital plane tilted from the common reference? That shared baseline is why the ecliptic works so well in navigation and in diagrams. A diagram can flatten the broad arrangement onto a page without choosing a line merely because it looks convenient. A navigator can describe positions and paths from the same reference instead of changing the baseline from one planet to another. The drawing is compact because the planetary orbits really do cluster near that plane, though the drawing itself does not explain how the cluster formed. So when we call the planetary system flat, we are describing a distribution. A cluster can remain a cluster even when its members do not sit precisely at its center. In the same way, a major planet can follow an inclined orbit without erasing the larger pattern. Flat does not mean that every orbit has zero inclination, or that every path lies inside one infinitely thin plane. This distinction also prevents the ecliptic from being stretched into a claim about every object in the solar system. Here, it describes the broad arrangement of the major planets. It gives their orbital tilts a common point of comparison, while leaving room for real differences among them. The remaining test is concrete. How far can one major planet depart from that reference and still belong to the same clustered system? Mercury gives us a measured answer. In the J2000 orbital elements, its inclination is about 7.01 degrees relative to the ecliptic. Inclination compares the plane of one orbit with a chosen reference plane. If the two planes matched exactly, the inclination would be zero. Mercury's orbit is instead tilted by roughly 7 degrees from that baseline. Mercury does not travel on the ecliptic as though its path had been drawn onto a perfectly flat surface. The labels attached to that number are part of the measurement. 7.01 degrees is a J2000 value, and the ecliptic is the reference plane used for the comparison. Without the reference plane, an inclination has no stated baseline. Without the named epoch, the orbital elements have been separated from the convention that defines when they apply. The number, therefore, cannot be carried around as a freestanding property called Mercury's tilt, with no further description. It tells us how Mercury's orbital plane is oriented in a particular set of elements, measured against a particular plane at a named epoch. And the result leaves the larger pattern intact. An orbit inclined by about 7 degrees can still belong to a group whose members cluster near the ecliptic. Mercury is far enough from zero to rule out the literal claim that all planetary paths lie in one infinitely thin sheet, yet close enough to fit the broad concentration of major planet orbits around the same reference. The ecliptic remains a useful way to describe that concentration, because usefulness here depends on the shared pattern, not on perfect alignment. We can now give the solar system's apparent flatness a more precise meaning. It is a statistical arrangement with measurable planetary variation, and Mercury supplies one familiar amount of that variation. But this single planet does not define one universal thickness for the whole solar system, and it cannot tell us how every smaller body is arranged. To make that distinction, the next comparison has to ask whether small body populations remain similarly close to the ecliptic or occupy a wider range of inclinations. And some of those smaller bodies do occupy a much wider range. Their orbital inclinations can be far larger than the inclinations of the 8 planets, extending well beyond Mercury's modest tilt. Inclination describes how much an orbit is tilted relative to a chosen reference plane, so a highly inclined orbit carries its body well away from the region where the major planets remain broadly concentrated. That changes the physical picture. If you look only at the 8 planets, the solar system resembles a fairly thin arrangement with measurable variation inside it. Add the more highly inclined small body populations, and the structure becomes more clearly three-dimensional. The planetary pattern is still real, but it is one population pattern inside a wider collection of orbits. Their inclinations can also carry information about orbital history. Dynamical scattering can redirect an orbit and change its tilt, while migration can alter the orbital arrangement in ways that also change inclinations. A body now traveling far above and below the ecliptic may therefore have reached that orbit through a history of gravitational change rather than simply occupying a fixed exception that has always looked the same. There is no single permitted history for every highly inclined small body. Scattering and migration are processes that can produce changes, but they should not be treated as one complete explanation for every individual orbit. Different populations and different members within them can carry different dynamical histories. The shared observation is the larger spread in inclination, not one universal cause assigned to all of it. None of this removes the ecliptic as a practical reference. It still describes the broad concentration of the major planets, and gives us a common plane from which inclinations can be measured. Its limit is simply clearer now. It is a strong guide to the major planet arrangement, not a claim that every object must remain close to that plane. The apparent disk is therefore a population pattern shaped by orbital history, with smaller bodies preserving a much wider set of paths through three-dimensional space. That wider spread of paths also clears away a misleading image. An orbital plane is a geometric reference, a way to describe an orbit's position and motion in three-dimensional space. It is not a sheet of matter surrounding the Sun. When an orbit crosses a reference plane, the spacecraft simply passes through a location defined by geometry. There is no wall there. Ulysses showed just how far an actual heliocentric orbit can lean away from a familiar reference. After a route assisted by Jupiter, the spacecraft entered an orbit inclined by 80.2 degrees to the solar equator. Its motion was physically possible because space did not contain a disk that had to be pierced. But Ulysses does not tell us that every spacecraft can reach such an orbit cheaply, directly, or under the same mission constraints. Its Jupiter-assisted route is part of the example. The absence of a material barrier removes one false difficulty. It does not remove the work required to establish a different state of motion. That work is described with velocity. Velocity includes direction as well as speed, so a spacecraft moving at the same speed before and after a maneuver can still undergo a large velocity change if its direction turns sharply. For an idealized, impulsive plane change in which the speed remains equal on both sides, the required delta v depends on that speed and on the angle between the old and new velocity vectors. A larger turn separates those vectors more, while the same angular turn demands a different delta v at a different speed. The exact numerical result belongs to the particular assumptions used for the maneuver, not to the mere fact that one orbit is drawn above another. So the broad concentration near a shared plane is not enforced by matter sitting in the way. It is a pattern in where many orbits ended up, while Ulysses confirms that much steeper heliocentric paths can exist. The remaining question is how the solar system's formation produced that broad clustering in the first place. That broad clustering began with the material from which the solar system formed. The solar nebula had net angular momentum. Its pieces did not all have to move in the same direction. Some motions could oppose others, yet the cloud as a whole still had a remaining rotational direction once those motions were combined. That shared remainder is what net means here. As gravity drew the material inward, the cloud did not lose that overall angular momentum by becoming smaller. The net rotation gave the collapsing material a preferred axis, rather like the central line around which the cloud's overall motion could be described. This was not an arrow pointing toward a special up in the universe. It belonged to this cloud and its history. Another rotating system could have an axis pointing somewhere else. An axis changes the geometry available to the material. Rotation takes place around it, so the directions perpendicular to that axis are physically different from the direction running along it. A broad, flattened arrangement around the axis can therefore emerge from material sharing that rotational organization. The corresponding plane is perpendicular to the preferred axis, and it supplies the physical ancestry of the broad orbital plane we now use when describing the solar system. So the ecliptic is more than a convenient baseline added to a finished diagram. It traces a population pattern back to the cloud that formed the Sun and planets. You can think of the present concentration of orbits near that plane as a surviving consequence of the nebula's net angular momentum, without turning the plane into a sheet of matter or a barrier that spacecraft must cross. That account has a firm limit. It explains why the system could acquire one broad preferred plane, but it does not assign every planet, asteroid or spacecraft its exact inclination, and it does not reconstruct every later orbit. Nor does rotation by itself explain how the gas lost energy or moved angular momentum around while the nebula changed. The axis selects the broad geometry. The unresolved physical step is how the material could settle toward a disk around it. For the cloud to settle, some of its energy had to be dissipated. Gas does not have to preserve every part of its initial motion unchanged as the cloud collapses and rotates. The material can lose energy during that change, so motions that carry gas away from the preferred plane do not have to continue forever. Rotation has already supplied an axis and a broad geometry. Dissipation allows the gas to move toward that geometry, rather than merely circling in a thick, unsettled cloud. A spinning bowl can suggest why a flatter arrangement belongs around a rotation axis, and a figure skater can suggest that changing shape and rotation are connected. But neither example supplies the missing physics. A solid bowl keeps its shape, while a skater is one connected body. The solar nebula was gas, and its parts could change their motions while the whole cloud continued to carry net angular momentum. The important addition is that energy could be lost as the material settled. That is what turns a flat-looking analogy into a possible physical history for a disk. Energy loss does not mean angular momentum simply vanished. Those are different parts of the account. Dissipation helps the gas settle into a flatter, rotating configuration around the axis chosen by the cloud's net angular momentum. The angular momentum still has to be retained, redistributed through the disk, or carried away by some physical process. So dissipation explains why settling is possible without pretending that it determines every detail of the disk's later development. The material also differed from water turning in a bowl in two basic ways. Protoplanetary gas was self-gravitating, meaning the gas itself contributed to the gravity shaping its behavior. It was also magnetized, so magnetic effects were coupled to the motion of the gas as the disk changed. Gravity, gas motion, and magnetic processes, therefore, belonged to the same developing system. A household object may preserve the visual intuition of flattening around an axis, but it cannot reproduce that behavior. Losing energy, then, did not leave the gas free to fall straight inward. Its angular momentum remained part of the motion. As the protoplanetary disk developed, that angular momentum could be redistributed through the material or carried away from the disk. The settling and the redistribution were coupled parts of the same change, rather than separate steps in which energy disappeared first and angular momentum became an afterthought. Turbulence is one possible part of that transport. Irregular motion within the disk can help pass angular momentum between different regions, while the gas and other material continue to move. This does not mean turbulence alone built every disk in the same way. It belongs to a family of processes that can alter where angular momentum is held as the disk develops. Magnetic effects add another root because the gas is magnetized and its motion is coupled to magnetic processes. Disk winds can also carry angular momentum away from the disk, instead of only shifting it from one region to another. Those roots connect the behavior of the disk's material with what leaves the disk, so its evolution depends on more than the loss of energy that first allowed the gas to settle. Migration belongs to this transport problem as well. As material moves through the developing disk, angular momentum can be exchanged and redistributed within the system. That makes the disk a changing arrangement of material and motion, rather than a finished shape produced at the instant the gas flattened. You can keep the broad image of rotation around a shared direction, while allowing the distribution inside that image to change. Meteorites give us something more direct than a plausible account of the solar nebula. They are traces left from the system's early history, and the evidence preserved in them limits which histories can fit. Researchers can use those traces to reconstruct parts of how the disk changed, even though no meteorite contains a complete record from the first stage to the last. The reconstruction begins with surviving material, rather than with a story chosen only because the physics sounds reasonable. Observations of disks around other stars add a different kind of constraint. They show disk systems that can be studied, while dynamical work tests how planet formation can proceed under physical rules. Those lines of evidence meet the meteorite record from separate directions. Together, they narrow the possible history of our solar nebula, but they do not produce one continuous, settled movie with every event placed in a final order. Some stages can be supported without every transition between them being known. That is where turbulence, magnetic winds, and migration have to be handled carefully. Each can take part in the development of a disk, but their relative shares are still being researched. The open problem is how strongly each pathway acted, how their effects were combined, and when each became important during formation. Different proposed histories can assign those roles differently, while remaining within the evidence that has survived. Uncertainty here belongs to the detailed route and chronology. It does not erase the broad result that needs explaining. The planets still occupy a broad orbital plane, and the rotating disk has a supported physical basis in dissipation and shared angular momentum. The plane is neither a solid surface nor a wall waiting above a spacecraft. It is the surviving geometry of where most of the system's large bodies formed and now move. For a spacecraft leaving Earth, that geometry is already present in its launch state. Earth carries it around the Sun within the broad plane. The unfinished history of how every formation process contributed does not remove that starting motion. Changing the direction of the spacecraft's orbit must still be paid for with a real change in velocity. That starting motion is fast. For a circular reference orbit at 1 astronomical unit from the Sun, the speed is about 29.78 kilometers per second. Earth carries a rocket around the Sun at roughly that scale before the rocket's engines add any departure velocity. In the Sun's frame, the rocket begins with the motion of the world it is leaving. In miles, that circular 1.0 reference is about 66,600 miles per hour, often rounded to 67,000 miles per hour in speech. That is the speed already directed along Earth's path around the Sun. Empty space does not remove it. Moving away from Earth changes the rocket's relationship to Earth, while the Sun still sees a craft that arrived with a large heliocentric velocity already built into its starting state. 29.78 kilometers per second, or about 66,600 miles per hour, is a clean reference value rather than a live reading for every launch. It describes a circular orbit at 1 astronomical unit. It should not be treated as Earth's exact speed at every position, the exact heliocentric speed of a particular spacecraft, a measure of launch performance, or the speed required to escape Earth. A real mission has its own state, when and where it departs, so that specific state cannot be replaced by the rounded reference. The reference still tells us what any departure calculation has to account for. A rocket is not choosing a direction from a motionless point beside the Sun. It is changing motion that Earth has already supplied, and a change in direction is itself a change in velocity. The result depends on how the rocket's added velocity combines with that inherited motion. What looks from the ground like simply going up is therefore part of a moving solar orbit from the first instant. The broad planetary plane is not blocking the rocket, yet leaving that plane requires the mission to alter the fast heliocentric motion it already has. A spacecraft leaving Earth carries that solar motion with it. Before departure, the spacecraft and Earth have been moving around the Sun together. When the engines make their decisive change, the spacecraft already has nearly Earth's heliocentric velocity. The exact starting velocity depends on the mission's real state, not one perfectly circular reference value. But it is already directed and already part of the calculation. The engines supply a change to that existing velocity. They do not clear it away and replace it with motion chosen from zero. Velocity is a vector, so direction belongs to the quantity along with speed. The departure contribution must be added to the sun-centered vector the spacecraft already has. Pointing along the inherited motion produces one result. Pointing against part of it, or away from the shared orbital plane, produces another. No single departure direction is built into this rule. A mission may need a contribution that is prograde, radial, out of plane, or some combination defined by its intended trajectory. Those labels describe how the contribution is oriented relative to the motion already present. They are not separate ways of beginning again. The solar trajectory comes from the combined vector. Escaping Earth answers a more local question. As the spacecraft gets away, Earth's gravity stops being the dominant reference for what happens next, and the sun-centered orbit becomes more useful. The gravitational influences do not switch over at one sharp border. Leaving Earth's local regime also does not remove the velocity the spacecraft shared with Earth. A vehicle can escape Earth's control and retain almost all of that inherited motion around the Sun. A direction seen from the launch pad cannot by itself tell you what happened to the solar orbit. Going upward from the ground describes the spacecraft relative to the nearby surface. The heliocentric question asks what change was added to a fast vector already present. To find the new path, place the departure contribution and inherited solar velocity in the same sun-centered frame, then combine them. That combined velocity also explains what an eastward launch can and cannot do. Earth is rotating beneath the rocket, so a rocket leaving in the eastward direction can begin with a modest contribution from the motion of the ground. The engines do not have to provide that portion themselves, and that can help launch performance. The contribution is real, though its size and value depend on the particular launch, rather than on a universal rule about which direction every rocket should follow. Earth's rotation around its own axis is separate from Earth's motion around the Sun. Before launch, the rocket already shares the planet's heliocentric velocity of roughly 29.78 kilometers per second, or about 66,600 miles per hour. Help from the rotating surface does not cancel that far larger sideways motion. Once the rocket is treated as an object orbiting the Sun, the inherited solar component remains part of its velocity. Now suppose the rocket is aimed away from the flat region in which the planets orbit. Its thrust vector can point out of the ecliptic, and that direction matters because thrust changes velocity along the direction in which it acts. Yet pointing the rocket there is only an orientation. At the instant the burn begins, the spacecraft is still moving around the Sun with the tangential component it inherited from Earth. The engine must run long enough to add an out-of-plane component to the full velocity vector. Turning the nose does not rotate the entire existing vector with it. This does not mean that a spacecraft must erase all of Earth's solar velocity before it can leave the ecliptic. An out-of-plane burn can change the direction of the resulting heliocentric motion, while much of the tangential component remains. How much change a particular burn supplies depends on the spacecraft's state when the maneuver occurs, where it is, how fast it is moving, and in which direction. Until those time-specific values are known in a sun-centered frame, the direction of the rocket's nose cannot tell us what the maneuver will cost. That time-specific description is called a state vector, and it needs more than a speed and a direction. It records the spacecraft's position and velocity at a particular date or epoch. A position measured from the Sun is not the same description as one measured from Earth, and a velocity only has meaning when we know what its direction and rate are being measured against. Without the epoch and the named frame, the numbers do not define the starting condition of an operational trajectory. The date matters because the planets do not hold still while a mission is being designed. Planetary ephemerids provide their positions and motions for a specified time, so they determine the exact geometry available when the spacecraft is meant to depart, encounter another world, or perform a maneuver. Change the epoch and the planets occupy different places along their paths. The spacecraft therefore begins with a different relationship to them, even if the mission's broad idea has not changed. Ephemerids are part of the calculation itself, because the geometry of a real route belongs to a date. We can still remove all of that detail when we want to see one piece of the physics clearly. In the circular 1-0 model, Earth is treated as following a clean circular path at one fixed distance from the Sun. That gives us a simple reference velocity whose direction can be turned on paper without claiming that a spacecraft could fly the resulting path. The model isolates the vector geometry. Begin with a defined heliocentric velocity, rotate it through some angle, and ask how large a velocity change that idealized turn requires under the stated conditions. What it cannot provide is a launch date, a complete route, a propulsion requirement, or the total velocity change for a mission. Those answers need the real epoch-specific state vector and the planetary ephemerides that go with it. The circular case has a narrower job. It lets us accept one clean initial vector as a bounded teaching model, then examine the geometry of changing its direction without confusing that demonstration with an operational trajectory. The initial vector gives us more than a speed. Velocity has a magnitude, which tells us how fast a spacecraft is moving, and a direction which tells us which way that motion points. Speed alone supplies only the first part. Two spacecraft can have the same speed while moving in different directions, so their velocities are different. For this teaching model, we can keep the clean heliocentric starting vector and examine what changes when its direction is turned. Picture each velocity as an arrow. Its length represents magnitude, while the way it points represents direction. Now draw a second arrow of equal length, inclined by some angle to the first. Equal lengths mean the speeds match, but the different directions make these different velocity vectors. Place their tails together, and the line from the first arrow's tip to the second arrow's tip has a length of its own. As long as an inclination separates them, that tip-to-tip length is not zero. That connecting vector is the change needed to replace the initial motion with the desired motion. We are comparing two complete states of motion, the heliocentric velocity accepted at the start and another heliocentric velocity inclined to it. The angle separates the arrows, and the separation between their tips gives the magnitude of the directional change. Delta V is the name for that required change in velocity. It belongs to the geometry of the two arrows, not to the empty space shown between a spacecraft and a plane on a diagram. A drawing may make the craft look higher as it travels, but that pictured distance does not define delta V. What must be priced here is the difference between the velocity the craft has and the inclined velocity we want it to have. This remains a statement about velocity change alone. It does not tell us a propellant mass, an engine size, or a fuel fraction, because those would require a specified propulsion system and a mass model. Within the bounded example, the useful quantity is now clear, the non-zero vector between the initial and desired directions of motion. Because the two velocity arrows have the same length, their difference has a geometric form. Place their tails together with the initial velocity along one side and the desired velocity along the other. The angle between them is delta I. The line joining their tips is the delta V the spacecraft must receive. For a single impulsive turn between equal speed velocity vectors, its size is delta V equals 2V times the sine of delta I divided by 2. You can see where that relation comes from by splitting the shape down the middle. The two velocity arrows, each with length V, form an isosceles triangle with the delta V line across its open side. Dividing it creates two matching right triangles. Each contains half the plane change angle, and each contributes V times the sine of that half angle to the open side. Put those two halves together, and a factor of 2 appears. The equation is simply the length of that joining line written in trigonometric form. Here, v has a narrow meaning. It is the common speed before and after the impulse. The spacecraft may leave in a different direction, but the length of its velocity arrow remains unchanged. That is why this expression prices only the turn. It does not include an increase or decrease in speed hidden inside the maneuver. If the initial and final speeds differ, the 2 arrows no longer have equal lengths, so this particular relation no longer describes the complete velocity change. Delta I is the defined angle between those 2 velocity directions. In this ideal case, it can also describe the angle between the corresponding orbital planes, because the impulse turns the velocity from one plane into the other. Both inputs are now visible: the speed the craft already carries, and the angle through which that velocity must turn. The relation applies only when that turn is treated as one instantaneous impulse with equal speeds on either side. A continuous low-thrust path, or a transfer that changes speed, needs a different trajectory treatment. At 1 astronomical unit, the circular orbit reference speed for this illustration is 29.78 km per second. That is the magnitude of each velocity arrow before and after the turn. The case holds that magnitude fixed and changes only the direction, so both sides of the calculation begin with the same inherited solar orbit speed. For a 90-degree turn, the angle placed into the equal speed relation is 90 degrees. The relation uses half of that angle inside the sine, which makes the calculation 2 times 29.78 times the sine of 45 degrees. The factor of 2 and a 45-degree angle come directly from the relation, while 29.78 km per second comes from the 1 reference speed. The geometry tells us why the answer is so large. The 2 velocity arrows have equal lengths, but one points at a right angle to the other. Delta V is the change needed to get from the first arrow to the second, not merely the final speed written down again. With 2 large perpendicular velocity vectors, the difference between them is also large. Carrying out that ideal calculation gives about 42.1 km per second. In miles per hour, the same velocity change is about 94,200 miles per hour. That conversion does not describe a second maneuver. It is the same 42.1 km per second expressed in a more familiar unit. The large number follows from turning a velocity that was already 29.78 km per second through a right angle while preserving its magnitude. The value belongs to a tightly defined case, an ideal, same speed, impulsive 90-degree turn at 1 astronomical unit. It is not the cost of launching upward from Earth, which is a different physical problem. Nor does this calculation supply an operational route. It isolates the directional change demanded when the separation between the initial and final velocity vectors is exactly 90 degrees. So the 42.1 km per second belongs only to that change between 2 heliocentric velocity vectors. It does not include leaving Earth's surface or escaping Earth's gravity. It does not include the energy lost while climbing through the atmosphere either. Those demands would have to be treated separately in any mission that began on Earth. And the demonstration says nothing about arrival at the other end. It gives no braking plan, no destination conditions, and no complete trajectory connecting departure to arrival. That also means the number cannot be placed beside a rocket's advertised total delta V, as though the 2 figures described the same job. 42.1 km per second is not a threshold that a spacecraft must cross before this kind of travel becomes possible. A complete mission budget depends on the propulsion system, the state from which the spacecraft departs, the chosen timing, and the path it follows. Change those choices, and you change the sequence of velocity changes the spacecraft must make. The single impulse in the illustration is another deliberate limit. It treats the entire right-angle change as if it happened at once, at 1 astronomical unit, while the spacecraft kept the same speed around the Sun. A real low-thrust spacecraft would accelerate gradually. Its thrust would act across time, while its position and velocity continue to change along the path. That extended trajectory cannot be reduced to the 1 instantaneous change used to construct the equal speed example. The illustration remains a geometric case, not a design for how an engine should perform the maneuver. What survives those limits is the specific lesson the number was meant to carry. A fast heliocentric velocity has both magnitude and direction. Rotating that vector through a large angle requires a large separation between the starting vector and the ending vector, even when their magnitudes are identical. In the 90-degree case, the 42.1 figure measures that separation. It is severe because the direction changes sharply while the existing heliocentric speed is already high. The 42.1 kilometers per second example describes the cost of turning one heliocentric velocity vector through a right angle. Solar escape asks a different question. It begins with a spacecraft already moving around the Sun on a circular orbit, then asks how fast that spacecraft must be moving there for the orbit to stop being bound. In the ideal two-body case, only the Sun and the spacecraft are included. The local escape speed is the square root of 2 times the circular speed. It does not say that every departing spacecraft follows a circular path, or that a real mission can ignore other bodies. The threshold comes from orbital energy. Below it, the spacecraft can travel far from the Sun and still remain gravitationally bound, with a path that can return. At the threshold, it has just enough total energy to become unbound in this two-body model. The word escape therefore names an energy condition. It does not name a direction on a diagram, and it does not mean that the spacecraft has crossed some distant physical border. For this comparison, the starting circle is fixed at 1 astronomical unit from the Sun. That is the heliocentric distance assigned to the calculation, not a complete description of a launch from Earth. Escaping Earth's gravity is a separate requirement because Earth is a different reference body. Crossing the heliosphere is separate as well. That endpoint depends on a boundary definition, whereas local solar escape depends on whether the Sun can keep the spacecraft bound. Once those limits are held in place, the comparison becomes precise. The spacecraft begins with the circular heliocentric velocity it already has at 1 astronomical unit. To reach the local solar escape threshold in the prograde case, the added velocity points along that existing orbital motion. The amount still required is the difference between the escape speed at that radius and the circular speed already present. That prograde increment is the quantity to calculate. Earth departure, heliosphere crossing, and a full operational trajectory remain outside this particular baseline. The added speed comes to about 12.3 kilometers per second. The push is prograde, meaning it points along the spacecraft's existing motion around the Sun. It adds to the velocity the spacecraft already has at 1 astronomical unit, raising the total to the local solar escape threshold. In miles per hour, the same increase is about 27,600. That is 12.3 kilometers per second expressed in another unit system. It is not a second burn or an extra amount to add afterward. Both numbers describe one change in speed applied in one direction from the same circular heliocentric reference orbit. The number follows directly from the relation between circular speed and escape speed in this two-body case. At a given radius, the local escape speed is the circular speed multiplied by the square root of 2. The spacecraft already possesses the circular part, so only the difference has to be supplied. Multiply the circular speed by the square root of 2 minus 1, and the result is that additional prograde speed of about 12.3 kilometers per second. Direction is the final distinction. Adding speed prograde increases the spacecraft's orbital energy until it reaches the local escape condition. Turning a velocity vector through a right angle is a different operation, even if both changes can be measured in kilometers per second. One raises the magnitude while preserving the direction of motion at the burn. The other changes direction. Keeping those actions separate lets the two numerical comparisons sit beside each other without suggesting that they describe the same maneuver. The prograde increment adds to the motion the spacecraft already has around the Sun. In the defined two-body comparison, the burn points along that motion, so the spacecraft leaves moving faster in the same direction. Its heliocentric orbital energy has risen. Add enough prograde speed, and it reaches the local solar escape condition used here. The plane change illustration prices another operation. At 1 astronomical unit, An ideal impulsive maneuver turns the heliocentric velocity vector through a right angle. Speed before and after the turn is equal. Draw those vectors as arrows, and they have the same length but point in directions separated by 90 degrees. Equal initial and final speeds do not make the plane change free. Delta V measures the change from the first velocity vector to the second. The prograde increment extends the existing vector in its current direction. The plane change must carry the tip of one equal length vector to another pointing sideways. Subtracting the two speeds as plane numbers would miss that turn, because the before and after arrows point in different directions. It receives a delta V value even though the final and initial magnitudes match, because direction is part of velocity too. The two values answer different questions. The local prograde figure tells us how much speed added along the orbit raises heliocentric orbital energy to the escape condition. The larger figure gives the vector change required to redirect an already fast heliocentric motion by 90 degrees while ending at the same speed. Both use kilometers per second, but their physical jobs are not interchangeable. This comparison does not choose a universal winner between escape and plane change. It compares one local prograde escape increment with one ideal, same speed, impulsive right-angle turn at one astronomical unit. A different turn, location, or trajectory would be a different case. Here, the apparent reversal has a limited cause. One number prices a tangential addition of orbital energy, while the other prices a large change in an existing velocity vector's direction. A spacecraft designer could not turn those two figures into a choice between two complete missions. 42.1 kilometers per second is the change required by the defined ideal vector rotation. 12.3 kilometers per second is the defined local increase associated with reaching the two-body escape condition. The comparison keeps one difference visible. Changing a velocity vector's direction is a different operation from adding enough local orbital energy for escape. Neither figure is a propellant total or a launch budget. An escape trajectory does not have to reproduce that single local calculation as its full route. Mission planners may consider low energy paths or gravity assists, and those choices bring their own exchanges among travel time, geometry, and operations. A gravity assist does not make escape free. It is one possible part of a route whose value depends on the constraints surrounding it, so the local 12.3 kilometers per second remains an illustration of energy, not a universal price tag. The same restraint applies to a mission seeking a large inclination. Its real route depends on what destination must be reached, what propulsion is available, which launch window is open, and how much risk the mission can accept. Those conditions cannot be folded into one general ranking. The positions and motions of the relevant bodies at the required time also matter, which means the trajectory must be treated for its specific ephemeris rather than prescribed from the 42.1 kilometers per second ideal turn. The ideal value still teaches something precise. Redirecting a fast-moving spacecraft through a large angle can require a very large change in velocity. Engineering, therefore, returns to routes under constraints. The two numbers separate direction cost from energy cost, but they do not declare that leaving the solar system is generally cheaper than going up. If high speed makes a large turn so costly, the next practical question is where along a possible trajectory the spacecraft can be moving more slowly. The direct plane change relation gives that question a precise answer. For an impulsive turn with the same speed before and after it, the required delta V contains the spacecraft's speed, v, as a multiplying term. Once the angle has been chosen, speed is not background information. It scales the velocity change demanded by that turn. Suppose the inclination change stays exactly the same, while the speed at the turning point becomes lower. The angular part of the calculation does not change, but the number multiplying it does. The direct plane change delta V therefore falls with the local speed. Redirecting a shorter velocity vector through a fixed angle requires a smaller change than redirecting a longer one. This is why the location of the turn can affect its price. A spacecraft does not travel at one unchanging speed everywhere along a possible orbit. That rule belongs to the plane change itself. It says what happens at the instant of the idealized turn, under the equal speed assumption used by the relation. It does not say how the spacecraft arrived at the slower point, what changes were required to place it there, or what must happen afterward. So a lower speed turning point can make the direct change of inclination smaller, while still failing to make the entire mission cheaper. Reaching that point may require other velocity changes. Speed alone cannot provide a total delta V, a propellant requirement, or a best route. It also cannot support a blanket rule that every mission should travel as far from the Sun as possible before changing direction. If two candidate turns make the same defined inclination change under this impulsive, equal speed relation, the one performed at lower local speed has the smaller direct plane change requirement. The earlier severe turn is no longer a verdict against going up. It tells an engineer to examine where the direction change occurs. The remaining question is which kind of orbit can provide a slower point where that turn could be made. A transfer orbit can provide that slower place. The spacecraft leaves the earlier point and follows a path on which its orbital speed changes. At a later point along that path, it may be moving more slowly than it was before. That later point then offers a different place to perform part of the inclination change. The advantage comes from the same speed dependence we have already followed. A plane change turns the spacecraft's velocity. When the local speed is lower, the direct plane change term for a given turn is lower as well. So a mission can arrange the trajectory so that some of the turning happens where the spacecraft is slower, rather than demanding the whole change at the earlier, faster point. This does not mean the transfer has erased the cost of changing direction. The slow point exists because the spacecraft took a particular route to reach it, and that route has its own velocity changes. Nor does every inclination change have to be saved for one later point. How much of the turn is moved, and where it is made, depend on the mission's defined path and constraints. What the transfer provides is a placement choice. It lets an engineer compare a turn made earlier at higher speed with a turn, or part of a turn, made later at lower speed. The local turning term can fall, but that comparison is incomplete until the velocity changes needed to create and leave the transfer are included. The slower point answers where the direction change might cost less. It does not yet answer whether reaching that point makes the complete trajectory cost less. To use that slower point, the spacecraft first has to follow a trajectory that reaches it. The mission must make the velocity changes that place the spacecraft on that orbit, then allow enough time for it to travel to the turning point. Those demands belong to the same route as the cheaper turn. They do not disappear simply because the spacecraft will be moving more slowly when it changes direction. The transfer has an energy demand. A turn at the slower point may require less velocity change than the turn made where the spacecraft is moving faster. Yet, that is only the local comparison. Engineers still have to include the changes that create the transfer and the changes needed afterward. Without a complete mission design, there is no defensible total or fixed propellant saving. Where the transfer places the spacecraft can matter as much as how slowly it moves there. A mission may need a particular viewing direction or encounter geometry for its science. The orbit chosen to produce a low-speed turning point may put that point in the wrong place, or bring the spacecraft there under geometry that does not support the required observation or encounter. The cheaper local turn may then conflict with the scientific path. Thermal limits impose a separate condition. The trajectory that creates the slow point must remain within what the spacecraft can tolerate, and a route acceptable for one design may be unacceptable for another. Time, science geometry, and thermal limits are not interchangeable penalties. A longer transfer might be acceptable while its geometry is not, or the geometry might work while the thermal conditions do not. Their relevance depends on the mission. The lower speed rule still answers a narrower question. What does the direction change cost at that location? The complete route includes the conditions that purchase access to the location. A locally cheaper inclination change is therefore not a free trajectory, and its value cannot be decided from turning speed alone. A planetary encounter offers another possibility, because it can change what kinds of turns are available. What can that encounter provide that an engine-only transfer cannot? That question cannot be answered by the plane change relation alone. The relation still tells an engineer how the cost of changing direction depends on speed at the point where the change is made. It can therefore compare particular maneuvers inside a proposed trajectory. But choosing the trajectory also depends on what propulsion the spacecraft has, and on the conditions available when it launches. A route that fits one propulsion system may be beyond another system's capabilities, even when both are aimed toward the same region of the solar system. Launch conditions can change which options are available from the start. The destination does not settle the choice either. Engineers must ask what target the spacecraft needs to reach, what scientific return the mission is meant to bring back, and how much risk the mission can accept. Those requirements can favor different ways of arranging the same kinds of velocity changes. A route should therefore be judged against a stated mission with its propulsion, purpose, and risk limits held in view. Without shared constraints, comparing Ulysses, solar orbiter, and a hypothetical direct route would turn unlike engineering problems into a misleading ranking. Time adds a condition that no speed rule can remove. Ephemerides describe where the planets will be, and that time-specific information determines whether the planetary geometry a route needs is actually present. A favorable encounter cannot be called up whenever a launch team wants one. If the planet is not in the required place during the mission's launch period, then that version of the route is unavailable, regardless of how attractive its plane change looks by itself. Waiting for different geometry may alter the launch conditions under which the whole design has to work. So the lower speed strategy remains one input with a precise job. It estimates the cost of a chosen change at a chosen place. Mission design decides where such changes can be placed within a trajectory after propulsion, launch conditions, target, scientific return, risk, and the ephemerides have all constrained the options. A moving planet can then be considered as part of that trajectory under the geometry that exists at a particular time. A moving planet can become part of the route, but first it helps to describe the encounter while treating that planet as the center of the view. In this planet-centered frame, the spacecraft arrives on a hyperbolic flyby. Its motion is described by an incoming planet relative velocity vector, an arrow that tells us how fast the spacecraft is moving relative to the planet, and which way that relative motion is directed. The word relative carries much of the meaning. This is not yet the spacecraft's motion around the Sun. As the spacecraft approaches, the planet's gravity pulls on it and bends its path. The velocity vector follows that bend. At one point, the arrow aims along the incoming part of the flyby. After the close passage, it aims along the outgoing part. The encounter has therefore changed the direction of the spacecraft's motion relative to the planet. Describing the event as a turn keeps the local mechanism clear. The spacecraft came in moving one way relative to the planet, and leaves moving another way relative to it. That is the precise piece hidden inside the familiar word slingshot. The planet is not behaving like an engine, and its gravity is not supplying fuel to the spacecraft. Nothing in this planet-centered description requires a burst of propulsion during the passage. Gravity redirects the incoming relative motion as the spacecraft moves through the encounter. Calling that redirection a turn also avoids giving the flyby a result that the planet frame account alone cannot establish. The wider route is measured around the Sun, however, and the planet itself is moving in that larger view. A turn that is clear in the planet-centered frame does not by itself tell us the spacecraft's final heliocentric velocity. It does not guarantee that the spacecraft gains energy in every frame, nor does it specify the eventual solar trajectory. To determine that result, the turned planet relative velocity must be considered together with the planet's own motion around the Sun. For now, the local event is exact and limited. An incoming relative velocity vector has been bent into a new relative direction. The planet is moving around the Sun as the spacecraft swings past it, carrying its own velocity through the larger, Sun-centered frame. The planet-centered and Sun-centered views describe the same encounter from moving standpoints. In one, the spacecraft arrives and leaves relative to the planet. In the other, both are traveling around the Sun. To find the spacecraft's outgoing velocity in that second frame, we add two velocity vectors. One is the planet's heliocentric velocity, its speed and direction around the Sun. The other is the spacecraft's outgoing velocity relative to the planet, after gravity has turned that relative vector. Adding them means combining their directions as well as their sizes. It is closer to adding 2 arrows than adding 2 readings on a speedometer. The same addition also applies before the encounter. The spacecraft's incoming heliocentric velocity is the planet's velocity added to the incoming planet relative vector. During the flyby, the planet's motion continues, while the spacecraft's relative vector leaves pointing in a different direction. Replacing the incoming relative arrow with the outgoing one changes the combined sun frame arrow. That is how a local bend measured near a planet can become a different path measured around the Sun. The result does not have to be a simple increase in speed. If the turned relative velocity points more along the planet's motion, the outgoing combination can have a greater heliocentric speed. If it points more against that motion, the combination can have a lower speed. Other turns may chiefly redirect the heliocentric velocity, changing where the spacecraft is going without producing the same kind of speed change. Speed and direction are separate parts of the result, even though one vector calculation gives us both. So the planet frame turn has a mission scale consequence once the planet's own motion is included. The spacecraft can leave on a different solar route from the one on which it arrived. The vector addition tells us what changed in the sun-centered description. It does not yet identify the physical source of that change, and that remaining account is needed before the flyby is fully explained. The physical source is the encounter with a planet that is already moving around the Sun. During the flyby, the planet pulls on the spacecraft, and the spacecraft pulls on the planet. If we draw the system boundary around both of them, their interaction conserves the system's momentum and energy. Here, energy means the total for the interacting system, including their gravitational interaction. The spacecraft can leave with a different sun-centered velocity because momentum and energy have been transferred within that larger system. Nothing has appeared from nowhere, even though the change can look that way when we watch only the spacecraft. The planet changes as well. Its motion after the encounter is not exactly what it would have been without the spacecraft, because the exchange has 2 sides. But the masses on those 2 sides are enormously unequal. A change that is large enough to redirect a spacecraft corresponds to an extremely small change in the planet's motion. That tiny response is easy to leave out of a mission diagram, while the spacecraft's new path may be the whole reason for the flyby. Leaving it out of the picture does not remove it from the physical accounting. This is what the word assist can hide. The planet does not hand the spacecraft free energy while remaining untouched. The encounter links the spacecraft to the motion of the planet, allowing the spacecraft-sized side of the exchange to show up as a different speed, a different direction, or both in the sun-centered frame. Depending on how the spacecraft approaches and leaves, the exchange need not give it a speed increase. A different arrangement can reduce its sun-centered speed or mainly turn its velocity instead. The exact result belongs to that particular geometry, so there is no universal bonus attached to passing near a planet. What remains constant is the accounting across the full planet spacecraft system. Whichever solar route the spacecraft takes afterward, its changed motion has a corresponding place in the conserved exchange. That accounting tells us why a gravity assist can change a solar orbit, but the result still depends on how the meeting happens. The spacecraft arrives with a particular velocity relative to the planet. Its approach geometry determines how the planet turns that relative velocity during the flyby. The spacecraft leaves on one specific path in the sun-centered frame. Change the direction of approach, or change the incoming planet relative velocity, and the outgoing path changes with it. The meeting must also occur at the right time. Planets keep moving along their own orbits, so a route that reaches a planet's orbital path does no good if the planet is somewhere else when the spacecraft gets there. Mission designers use ephemerides, which establish where the planets will be at particular times, to find encounters that can actually take place. The timing and approach must produce the needed turn. Even then, the strongest available turn may not make a workable mission. The encounter has to send the spacecraft toward the scientific target the mission was built to study, while remaining compatible with the conditions under which the spacecraft can be operated. A geometry that helps one part of the route can leave the later path poorly suited to the science objective or conflict with another operational limit. Designers therefore have to consider the flyby and the rest of the mission together. The planet is one moving part of a complete trajectory, not a free change of direction added afterward. So an encounter with a planet cannot supply any chosen inclination change whenever a spacecraft happens to pass nearby. A possible flyby by itself does not establish a viable route either. That claim requires an ephemeris-based design for a particular spacecraft approaching a particular moving planet at a particular time, followed by a path that still serves the mission. For the mission case ahead, that particular planet is Jupiter. Its usefulness comes from the encounter that can be designed with it, not from a general promise attached to the planet's name. That is how the route for Ulysses began. Although the mission would reach high solar latitudes, the spacecraft launched toward Jupiter. Its first destination was out along the solar plane, where the planet was moving through the place and time chosen for the encounter. If you only look at where Ulysses later traveled, that opening leg can seem like a detour. In the actual mission design, it was the way in. Jupiter had been selected as the gravity assist partner for the spacecraft's heliocentric trajectory. That wording is precise. The planet was a moving partner in a particular path around the Sun, and the path had to carry Ulysses to the encounter under the required geometry. Jupiter was not simply waiting above the solar system to give the spacecraft an upward push. Ulysses first had to travel toward the planet on the designed approach. This connects two parts of the mission that are easy to separate in your mind. One is the initial trip to Jupiter. The other is the high solar latitude Ulysses reached later. They belong to one route. The later path does not show that the spacecraft was launched directly above the solar plane. It shows what became possible because the mission was designed around an intermediate planetary encounter. That distinction also changes what the phrase "going up" can mean here. A launch direction alone does not describe the mission. The spacecraft begins on one heliocentric path, meets the selected moving planet, and then continues on another part of the planned route. For Ulysses, the geometry begins by sending the spacecraft toward Jupiter, even though the scientific destination that makes the mission memorable lies far from the planetary plane. None of this makes Jupiter the required partner for every mission seeking a high inclination, or proves that it would always be the best choice. The supported claim is narrower. Ulysses used Jupiter as its selected gravity assist partner, and its flight toward that planet was the necessary opening leg of this design. The next detail is therefore attached to a real encounter at a particular time, rather than to a spacecraft merely rising away from the planets. Ulysses flew past Jupiter on the 8th of February, 1992. That date pins the planned route to the encounter that changed the mission's path. The spacecraft had not simply been sent toward a distant planet and then onward by chance. Its meeting with Jupiter redirected its path around the Sun. The path being changed was heliocentric, meaning it was an orbit around the Sun. Jupiter did not give Ulysses a simple upward boost, as though the solar system shared one fixed direction called up. After the encounter, the spacecraft continued in a new Sun-centered orbit at a steep angle to the Sun's equator. The resulting orbit had an inclination of 80.2 degrees to the solar equator. Inclination is the angle between an orbital plane and a chosen reference plane. Here, that reference is the Sun's equatorial plane. The number does not describe a universal tilt, and it should not be reassigned to the ecliptic without a separate established relation. It belongs to one precise comparison, Ulysses's orbit against the solar equator. An angle of 80.2 degrees places the orbit close to perpendicular to the Sun's equatorial plane. This was the consequence of the Jupiter redirect. Ulysses was no longer confined to a path near that plane. It had the highly inclined solar orbit needed for its later passage over the Sun's polar regions. 80.2 degrees is the inclination of the complete orbit. It is not Ulysses's heliographic latitude at every point, or a label for how high the spacecraft was at one instant. Latitude changes as the spacecraft moves along the path. Inclination describes how the orbital plane is oriented relative to its reference plane. This result belongs to the planned Ulysses encounter. It does not establish that another mission using Jupiter would leave with the same inclination. What the flight fixes is exact. On the 8th of February, 1992, Jupiter redirected Ulysses into an orbit inclined 80.2 degrees to the solar equator. That orientation gave Ulysses a path through solar latitudes that spacecraft usually never reach. Heliographic latitude is measured from the Sun's equator, just as latitude on Earth is measured from Earth's equator. But it describes where Ulysses is along its orbit, not the tilt of the whole orbital plane. The plane kept its 80.2-degree inclination, while the spacecraft's latitude changed continuously as it moved around the Sun. Near the solar equator, its heliographic latitude was low, even though the orbit itself remained steeply inclined. Farther along the same path, Ulysses moved farther north or south of that equator. Over each solar pole, it reached 80.2 degrees of heliographic latitude. The same number therefore described two related things at the extreme: the plane's inclination relative to the solar equator, and the spacecraft's highest latitude as it passed above the Sun's polar regions. One is a property of the orbit's geometry, the other tells you where the spacecraft had traveled within that geometry. So the high-latitude route was real. Ulysses did not merely point an instrument toward the poles from the flat plane of the planets. It physically traveled through the regions above both poles, giving that 80.2-degree inclination a direct observational meaning. If up means moving far north or south of the solar equator, then a spacecraft has done it. Yet Ulysses remained in a bound orbit around the Sun. Its polar passages were parts of an elongated path that carried it away again, brought it back, and allowed the high-latitude motion to repeat. It had not escaped the Sun, and the achievement does not mean that a spacecraft can cheaply turn upward from any starting orbit. Jupiter had redirected this particular mission onto this particular path. That is the bounded correction to the literal claim of impossibility. Travel far outside the usual planetary plane is possible, and Ulysses reached the measurement that makes the point exact: 80.2 degrees over both solar poles. What made it possible was an engineered solar orbit, still held by the Sun, with a shape that returned the spacecraft to those high latitudes again. The orbit that produced those repeated high-latitude passages covered a wide range of distances from the Sun. Ulysses came as close as 1.34 astronomical units and went as far as 5.4 astronomical units. Those two distances belonged to the same ellipse. Its distance changed as it continued around the Sun, so the path that carried it over the polar regions also carried it through more distant parts of its orbit. Completing that route took about 6.2 years. That period describes the full cycle of this particular solar orbit, including the long movement away from one high-latitude passage and the eventual return. It gives the achievement a scale that the angle alone cannot give you. Reaching 80.2 degrees was one part of a route measured across years, rather than a quick turn followed by a permanent polar station. The spacecraft had to keep following the ellipse that Jupiter's redirection had given it. The ellipse was inclined in a way that carried Ulysses through both solar hemispheres. It passed through high northern and high southern latitudes as it moved around the Sun, instead of staying above either pole. So over the poles describes where the spacecraft traveled during portions of the orbit. It does not describe a fixed perch where Ulysses could watch one pole continuously. Each passage was part of the same repeating motion, with the spacecraft continuing onward after it crossed the high-latitude region. That distinction also limits what Ulysses can tell us about other missions. Its range from 1.34 to 5.4 astronomical units, its roughly 6.2-year period, and its movement through both hemispheres describe the orbit Ulysses actually flew. They do not establish that the same route would suit another launch date, another propulsion system, another scientific goal, or another encounter geometry. Ulysses showed that a bound spacecraft could attain high solar latitude through a carefully shaped, inclined orbit. The cost appeared in the shape itself: a long ellipse, large changes in distance, and years spent completing each circuit. Solar Orbiter takes a different path to high solar latitudes. Ulysses used Jupiter for the encounter that placed it into its long, steeply inclined orbit. Solar Orbiter returns to Venus more than once, using those flybys to raise the inclination of its orbit around the Sun in stages. The change is accumulated across a sequence, rather than delivered through a single Jupiter encounter. Each return to Venus has to fit the motion of the planet and the spacecraft. Venus keeps circling the Sun, while Solar Orbiter follows the orbit shaped by its earlier encounters. Mission timing brings those paths together again. Orbital resonance helps arrange that pattern. After a planned interval, their motions place Solar Orbiter and Venus in the geometry needed for another encounter. A flyby belongs to a timed chain, with one return helping establish the path toward another. That sequence is what lets the inclination build incrementally. At an encounter, Solar Orbiter's path is redirected so that its following orbit can carry it at a greater angle to the plane in which the planets travel. A later Venus encounter can then add to what the earlier route has already produced. The encounters aren't interchangeable events that could be moved to any date. Their order and timing are part of the route itself, because every new approach begins from the orbit left by the previous stage. Venus, therefore, plays a specific role in Solar Orbiter's mission design. This isn't a general rule that any spacecraft can use Venus to gain whatever inclination it needs, and it doesn't mean the spacecraft is climbing straight upward from the solar system. It remains in orbit around the Sun, while the orientation of that orbit changes through the planned sequence of encounters. The contrast with Ulysses is precise. One mission reached its high-latitude path through a single Jupiter-assisted route, and then followed a long ellipse. Solar Orbiter uses repeated Venus encounters to increase inclination step by step. That distinction also separates what its completed encounters and present orbit have allowed it to observe from what later encounters are intended to make possible. After its Venus flyby in February 2025, Solar Orbiter put that step-by-step route to use in observations made the following March. During those observations, it reached a maximum viewing angle of 17 degrees. This was something the mission had already achieved, rather than a goal waiting for another encounter. The repeated work with Venus had changed the geometry enough to move the spacecraft's line of sight beyond the familiar plane. 17 degrees may sound modest beside the steeper figures associated with other missions, but the observation gave that number a physical meaning. What came back was the first view of a solar pole made from outside the ecliptic. Crossing beyond that plane changed which part of the Sun's solar orbiter could see. The pole was no longer being viewed only from within the ecliptic, so the 17-degree maximum was more than a number attached to the mission. It was the angle that made this view possible, and the returned observation showed that the incremental route had produced a result. The comparison with Ulysses still has a firm limit. Ulysses reached a solar orbit inclination of 80.2 degrees, while Solar Orbiter's March result was a maximum viewing angle of 17 degrees. Those measurements describe different geometry. One gives the inclination of Ulysses's orbit, the other gives the angle from which Solar Orbiter observed. Treating them as versions of the same measurement would make Solar Orbiter seem to have reached a path it did not reach. Solar Orbiter was not looking straight down from above the Sun. Its first polar view came from a much lower angle outside the ecliptic, and that distinction is part of the result. Ulysses and Solar Orbiter both addressed high solar latitude, but their achieved geometry and observational aims were not interchangeable. For Solar Orbiter, the result from March 2025 was narrower and specific. A 17-degree view outside the ecliptic had already been enough to see a solar pole for the first time. That 17-degree view belongs to the mission's record of completed observations. The larger angles on ESA's trajectory schedule belong to the future, and reading them that way changes what we can say about Solar Orbiter. They describe where the mission is intended to go next, rather than extra views it has already sent home. ESA lists another Venus flyby for the 24th of December, 2026. That flyby is aimed at giving Solar Orbiter a viewing angle of about 24 degrees. The date, the flyby, and the angle form one planned step. They do not mean that the spacecraft has already reached 24 degrees, and the word about belongs with the target itself. Even if the flyby occurs on the listed date, the schedule does not turn its intended geometry into a completed observation in advance. The same distinction applies farther along the route. ESA's later trajectory targets aim toward a viewing angle of 33 degrees. 33 degrees is therefore a direction for the later mission plan, not a measurement that can be placed beside the achieved 17-degree view, as though both were observations already returned. The increase from about 24 degrees toward 33 degrees also tells you why the Venus sequence continues. Each planned stage is meant to move the viewing geometry farther away from the ecliptic, but the evidence here supports the targets on ESA's schedule, not their achievement. ESA adds a direct limit to how firmly that future schedule can be read. The listed trajectory dates are subject to change, so the 24th of December, 2026, should remain attached to the currently listed Venus flyby without being treated as a guarantee. The later 33-degree targets carry the same future status. A revised date would change the timing of the plan, while leaving the earlier 17-degree observation where it belongs, as something Solar Orbiter had already accomplished in March 2025. That separation between what has happened and what remains scheduled becomes clearer when Solar Orbiter is placed beside Ulysses. Ulysses used a Jupiter flyby to enter a highly inclined solar orbit with a long period. Jupiter was therefore part of the route that changed the mission's solar orbit geometry. The result was a path reaching far from the planetary plane, but still a solar orbit. A large change in inclination did not, by itself, turn Ulysses into a spacecraft escaping the solar system. Solar Orbiter is following a different route. Instead of using Jupiter to enter the kind of orbit flown by Ulysses, it uses a sequence of encounters with Venus to raise its viewing latitude gradually. That gradual increase is part of the mission design. One encounter belongs to a continuing series, with achieved viewing angles kept separate from angles assigned to later encounters. So its path should be described through the latitude it has already reached, and the further changes still on the schedule, rather than treated as a completed copy of Ulysses. The contrast comes from the constraints of the two missions. Ulysses had a Jupiter flyby available for its move into a highly inclined, long-period orbit. Solar Orbiter has repeated Venus encounters available for a step-by-step increase in viewing latitude. Those planetary encounters do not provide one standard route that every mission could simply choose. They give each spacecraft a particular set of opportunities, and those opportunities meet different mission objectives. That is why the missions do not belong in a ranking based on one shared measure. Solar Orbiter is not a failed Ulysses, and Ulysses is not the only serious attempt to observe the Sun from high latitude. Each mission uses the planetary geometry available to pursue its own objectives. Both paths move away from the familiar geometry of planets circling close to the same plane. Neither path, merely because it changes the angle from which the Sun is approached or viewed, automatically crosses every boundary people may mean when they speak of leaving the solar system. Going up within a changed solar orbit is different from going out. In this case, up has a precise geometric meaning. After its Jupiter flyby, Ulysses entered a heliocentric orbit inclined by 80.2 degrees to the Sun's equator. That steep angle carried the spacecraft over high solar latitudes. Yet Ulysses was still in orbit around the Sun. Its path had changed direction without becoming a route out of the solar system. An inclination needs a plane to be measured against. For Ulysses, the stated angle uses the solar equator. Another plane that appears often in descriptions of the solar system is the ecliptic, the reference plane defined by Earth's orbit around the Sun. When someone says that an object is above the ecliptic, above means that the object lies on one side of that selected plane. Below means the other side. The words give us a location relative to a coordinate system. They don't identify a physical surface in space. You can see why the language is easy to misread. On Earth, going above something often means climbing past a solid object or leaving the ground behind. A reference plane has no material to pass through. A spacecraft crossing the ecliptic would encounter no floor, ceiling, shell, or rim there. It would simply move from one side of the plane to the other, while gravity continued to shape its orbit. The same distinction applies when the whole orbit is highly inclined. Inclination describes how one orbital plane is tilted relative to the plane chosen for comparison. It does not, by itself, say that the orbit is unbound, that the Sun no longer controls the motion, or that the spacecraft has crossed the outer reach of the Sun's surrounding environment. Those are separate claims, and each needs its own evidence and its own boundary. So Ulysses could travel far above a familiar plane and still remain on a sun-centered path. high latitude answers a question about direction and geometry. Leaving the solar system requires us to name what the spacecraft is supposed to leave: a sun-bound orbit, the region shaped by the solar wind, or some more distant limit. A plane alone cannot answer that. Once a spacecraft escapes Earth, the reference for its motion changes. It is no longer on a path bound to Earth, so the Sun becomes the primary gravitational reference. It has not escaped the solar system. Earth itself travels around the Sun, and a spacecraft leaving Earth can continue on its own Sun-centered orbit. One bond has ended while another remains. Escaping the Sun is a separate physical condition. In a simplified model, begin with a spacecraft moving in a circular orbit around the Sun. Its energy is not enough to leave the Sun permanently. Solar escape requires additional energy so that the path is no longer bound to the Sun. This simplified two-body comparison is not a complete design for a real flight. It also is not defined by turning towards some special direction. Changing the direction of an orbit and supplying enough energy to escape answer different questions. The heliosphere gives the word out another meaning. It is the region around the Sun shaped by solar conditions, so reaching one of its boundaries is a crossing through the Sun's surrounding environment. But the location of such a boundary can depend on the state of the Sun, and its meaning depends on which definition a speaker has chosen. There is no single fixed line that settles every possible meaning of the solar system's edge. These endpoints can therefore occur without standing in for one another. A spacecraft may stop being bound to Earth while remaining bound to the Sun. A solar escape path answers whether the Sun can retain the spacecraft gravitationally, while a heliosphere crossing answers whether it has crossed a defined environmental boundary. Neither question is the same as asking how far above a chosen plane the spacecraft has traveled. So, outside the solar system is incomplete unless we name the reference. Do we mean free from Earth, unbound from the Sun, or beyond a specified heliosphere boundary under the conditions then present? Each destination requires its own physical test. The word up supplies only a direction relative to something else. It cannot choose the endpoint or prove that the spacecraft has reached it. Close to Earth, up still has a clear physical meaning. It points along the local vertical, radially away from Earth's center. That direction changes as you move around the planet, because every location has its own radial line, yet the reference remains unambiguous. Earth is the body that defines it, so a rocket can rise from a launch site without pretending that the same arrow applies everywhere in space. Far enough from Earth, the request has to become more specific. If you want a spacecraft to travel out of a plane, you must name the central body and a reference plane. A path tilted relative to Earth's equator is a different request from one tilted relative to Earth's orbit around the Sun. Neither is a universal upward direction. Each is a trajectory described in a stated frame. The way the spacecraft is pointing must also stay separate from the way it is moving. Turning the spacecraft changes its attitude. Changing its path requires a change in velocity. For a large change in heliocentric inclination, that velocity is already sun-centered and has to be turned. In the idealized case where one instantaneous maneuver changes direction while keeping the same speed, the required delta V grows when the angle of the turn grows. It also grows when the spacecraft is moving faster. A perpendicular-looking destination can therefore demand a large velocity change, even though no wall or forbidden region lies above the original plane. The cost comes from redirecting inherited motion, not from fighting a cosmic version of height. That idealized plane change is a way to expose the mechanism, not a launch prescription. High-inclination solar orbits can be flown, and up has not stopped existing wherever a named body supplies a local vertical. But there is no single delta V for going up in the solar system. A real answer must specify a date and ephemeris, the propulsion model, the target, and the mission constraints. Once those are named, the loose direction becomes a defined geometry and a required velocity change. Until then, up tells us too little to design the trajectory. Near Earth, up still has a meaning. It points away from Earth's center, while down points back toward that center. The direction changes because the radial line changes with you. Two people far apart can both point up, even though their fingers aim into different parts of the sky. Earth supplies the reference that makes both directions valid, so the word has not failed us. It is local, tied to the body whose gravity and shape define the vertical under your feet. The solar system gives us several other reference geometries, each chosen for a different job. The ecliptic follows the geometry of Earth's orbit. The solar equator belongs to the Sun's rotation. The invariable plane is another defined plane for describing the system. These references let astronomers and mission designers state positions and motions precisely, but none becomes a universal horizontal. A trajectory can sit above one plane, cross another, and be described differently from a third. Calling one side up only works after you name the reference. The plane is part of the question, not a flaw built into space. Ulysses made that distinction physical. Its route used an encounter with Jupiter to enter an orbit that carried it far from a selected plane. Solar Orbiter is pursuing high solar latitudes through a route assisted by encounters with Venus. Those missions did not discover a hidden vertical passage. Their trajectories were designed around the bodies available to assist them, and the constraints each mission had to meet. Nor can their paths be placed on one simple ladder and ranked by a single inclination number. They are separate solutions to separate orbital requests. That is why going far from a plane is possible without becoming a simple ascent. A mission first declares the body and plane that give its words meaning, then works out which part of its velocity must change, and how the permitted trajectory can produce that change. Near home, up is the radial direction Earth gives you. In orbital design, the same word has to arrive with two details attached: up relative to what, and what velocity must change.